Здравствуйте.
Привет. Сегодня
М,
будем на английском.
Да,
Тамара обещает прийти.
я, я вроде бы попытался сделать раскладку, с помощью которой можно вводить CV-знаки.
Так, а ты помнишь, что мы сегодня занимаемся формальной семантикой?
Я помню, да, но я хотел рассказать
Хорошо.
можно?
Мгм.
Ну да, и я ее поставил, и по каким-то загадочным причинам единственный символ, который она вводит, это единичка. А все остальные символы в ней вроде бы есть, но почему-то не отказываются вводиться.
Эх. Окей. People start gathering. Um, Marcelo was talking about the Hittite stuff we discussed 1 week ago. So nothing to do with formal semantics. And so I don't know actually, and I'm not exactly ready to discuss it now, okay? Let's discuss it tomorrow.
Окей,
Mhm. I'll think what I can answer, and I'll check in the morning if I can suggest anything. I mean, that's really not my strongest thing, actually. All right. Um, we're waiting for at least Wien, but hopefully all the others. Let me check if Wien's here. Wien doesn't answer, doesn't um hopefully he exists somewhere, but he doesn't answer, doesn't reply. Right. I suggest we start and people follow up and watch the recording if anything. Okay, so last time I remind you we were talking about functions, but before we went into functions, we were talking about reciprocity and symmetry hypothesis. And there was this task on page 78. I'm going to share my page. Okay, this thing. And we sort of couldn't even understand what we asked to do. So, so I wanted to discuss it, explain it, here again. So the task in this problem 23 is that we have a list of nouns. You remember mother, sister, spouse, dog walker, secret admirer, wife, and so on. And these nouns name relations. Okay? So, and we have sentences like A and B are ends. And sometimes it has a reciprocal reading, like A is N of B and B is N of A. For example, we got Peter and Mary, they are siblings. So Peter is a sibling of Mary and Mary is a sibling of Peter. This is reciprocal reading. The symmetry hypothesis says you get that reciprocal reading only if the relation named by the noun is symmetric. If A is N of B, then B is N of A. This works with siblings, but this doesn't work with, for example, wives. Oh, okay, let's say secret admirers. Okay, secret admirer is not symmetric. Yeah, so in this task, we had to check for each noun if we have this symmetry. Yeah, and we have to sort nouns into true positive, false positive, true negative, false negative. And I remind you that it's, well, true is when the prediction gives true. Like if we expect that the relation is symmetric, it's true, and it is symmetric, it's true positive. If we expect that the relation is not symmetric, and it is indeed not symmetric, it's true negative. If we expect that it is symmetric, but it's not, it's false positive. And if we expect that it's not symmetric, but it is, then it's false negative, just to remind you. So, if the sentence A and B are ends, for example, siblings, wives, spouses, and so on, secret admirers, feels like a natural answer and means each to the other, then the noun allows a reciprocal reading. For example, A and B are siblings, Peter and Mary are siblings, feels like a natural answer and means each to the other. But A and B are secret admirers doesn't feel like a natural answer, right? Something more. Okay.
No, it sounds like a normal. Ah, oh, sorry.
We need means to each other. Yeah, they cannot be secret admirers to each other. Okay. So secret admirer is truly non-symmetrical. Okay. So we have true positives here in the list. True positives, well, it's good and predicted good, meaning we expect that it is symmetrical, meaning it gives true, it renders true. And yeah, it is indeed symmetric. Hi, Sonia. We're discussing exercise 23 when the task was to to look at the list of those nouns like mother, sister, spouse, dog walker, wife, secret admirers, and so on. Um,
Mm-hmm.
and we were checking if they have a reciprocal reading, and we apply symmetry hypothesis, and we sort nouns into true positive, false positive, true negative, false negative. Okay?
And what are the results? What you called true positive?
Okay, that's where we are now.
Mm-hmm.
So, true positives, good and predicted good. Sibling, spouse, acquaintance.
Mm-hmm.
Okay?
Mm-hmm.
These relations are naturally symmetric. So A and B are siblings or spouses or acquaintances, works reciprocally. Now, true negatives, meaning bad and predicted bad. Dog walker, mother, secret admirer. These are asymmetric or weird as mutual, like walker versus walked, parent versus child, secret makes mutuality really odd.
Mm-hmm.
Now we come to the false ones. False negatives. False negatives are good, but predicted bad by plain symmetry, by the symmetry hypothesis. These are sister and wife from our list. The best symmetry test treats them as asymmetric, okay, because they're gendered rows. But in context, we usually restrict the domain. You remember we restricted it that the person should come out of the set of males or females, where each, so we restrict the domain to pairs where each can satisfy the role to women, and then the relation is symmetric indeed. So this gives us a built-in presupposition plus domain restriction, and this is where we switch on Strawson symmetry. Okay, and Strawson symmetry fixes the well, it's called undergeneration. I mean, when it's predicted bad, but it actually good. Predicted false, but renders true. I mean, when we have two sisters or we have a married female couple, yeah, then we have a symmetric for sisters and wives. Right, these are false negatives. Yeah, so they're predicted as false, but in fact they're true. That's false negatives. False positives, actually, we do not have false positives in the set. Yeah. So the symmetry hypothesis works not that good, not that well, like it underpredicts for gendered kin terms like sister and wife. Yeah, so, and once we assume the appropriate domain, female in this case, the reciprocal reading is fine. That's what we discussed last time, and this is what this task is about. Okay, and then we were talking about the Strawson symmetry hypothesis. We limit the domain for example, males for brother or females for sisters, and then symmetry starts working, and then we get a reciprocal reading. All right. And we were talking about functions, and I just wanted to remind you that a function is a relation. Not every relation is a function, but every function is a relation. We call it relation as R from A to B, okay? Where A is an argument and B is an value, yeah? A is input, and we call inputs arguments, and B is a value, and we call values, B is an output, and we call outputs values. Right. And a relation R from A to B is a function if and only if every element of A has one and only one image in B. Like, for example, height of a person is a function because every person has only one height, do not have several, cannot like change its height. Whew. And sister, for example, is a relation but not a function because one person can have multiple sisters. Right. So we have a domain inputs A, and we have codomain potential outputs B, and each entity in the domain A, right, appears only once on the left and has exactly one arrow to B. Okay, so we have something like, I'm just trying to remind you, for example, we take height, and for example, Seva has, Seva, what's your height?
אני לא זוכר, סליחה.
Come again? What's your height? How tall are you?
He said אני לא זוכר. He doesn't remember.
Okay. Let's say
I would say
175.
75, yeah, around
Yeah,
75.
something. Yeah, Tamar. Okay.
What's my height?
Yeah, can you give us your height?
65?
65, for
Question
example.
mark?
Yeah, Masha, 67. Yeah, so we have each entity only once appeared on the left side, and it's got only one arrow to the B side. Yeah, and this is the way how we can describe this function, or we can describe it with F thing. F, for example, Seva is 175. Okay? Yeah, we can describe it in this way. Height of Seva is this way. Yeah, that's what we're were talking about, yeah, domain, codomain, domain, codomain, and these are let me see. This is not a function, and this is not a function because some of A's have two meanings, and this is not a function because this one does not have an arrow, a connection. And these two are functions because every A has got its meaning. And it can be the same meaning, actually. For example, for example, Tamara and I are close in height, so we can be said like having the same meaning in height, but it's always only one arrow from A to B. Yeah, these are functions, and we actually solved exercises, and we got to the propositions, propositional logic. Right. Do you remember where we stand? Or did we decide to start from the beginning? So do you remember? No? Okay. I suggest we're starting here. Propositional logic. Right. So well, what we're saying, what we mean actually, should predict that the following that we're saying is valid. Yeah. For example, if it rained last night, then the lawn is wet. Yeah. It rained last night. Okay, well, look. Yeah, indeed, the lawn is wet. So, the argument is valid. Every man is mortal. Socrates is a man. Socrates is mortal. Valid. Yeah. And and we're trying to formalize this logic. It goes like if one thing, then we have a consequence, right? So and now we come to, if it rained last night, then the lawn is wet. The lawn is wet, so the conclusion is it rained last night. Okay, is this argument valid?
No, it is.
Not necessarily.
Not necessarily.
Not necessarily.
Okay, so, and here our premises can be true, but the conclusion is false, right? It might be true, but if someone came and just used a hose, yeah, the lawn would be wet, but with no rain. Right. So this is a fallacy. If P then Q, we are given Q, but we do not have P. P does not renders, is not true. Yeah, and we're given more vocabulary here. Yeah, terms. P here is called the antecedent, and Q is called the consequent. And the policy, when the argument is not valid, is because the consequent is affirmed as premise and is then used to derive the antecedent. All right. Do you have any other fallacious argument using affirming the consequent? Can you think of such arguments?
Yes. 2 plus 2 is 4. 3 plus 3 is 6. Sun is cold.
That's not policy. That's not about that. Okay. It's, well, see, here we're talking about
all people are siblings, but not all siblings are people.
yeah.
Maybe cats siblings, horses siblings.
If we need if, okay? If well, okay, all siblings are people, right? If Peter is a sibling, he is a person. This is correct, right? No fallacy. Okay, but then Peter is a person. This does not lead us to, should not lead us to the statement that, okay, Peter and Mary are siblings. Okay, even if, one moment. Okay, siblings are people. Peter is a sibling of Mary, for example. Yeah, when we say that Peter is a person, yeah, this is absolutely correct. Because antecedent goes before the consequent. But if we put it like one moment, what did I say? Peter is a person, then Peter is a sibling. Then we put consequent before the antecedent, and we get a fallacy. Okay? Am I correct? If we say, for example, all cats meow. Okay? So, Ginger is a cat. So, Ginger meows. Okay? This is correct. This is okay. Now, we say Ginger meows. So Ginger is a cat. Is a cat. Yeah, this is a fallacy because Ginger might be a man who just meows. Meow, meow, I can meow as well. Okay? Masha meows, but Masha is not a cat. Yeah? Are we good so far?
Yeah.
Yeah. Right. Okay. And we're starting translating sentences into propositional logic. Okay, and this is a theory of entailment for natural language. All right, look at exercise 3. If it rained last night, then the lawn is wet. The lawn is not wet, therefore it did not rain last night. Okay, valid or fallacy?
Valid, I believe.
I think so, right?
Right.
Because
Yes. The lawn is not wet because if it rained, then it must have been wet.
yeah.
Therefore, it did not rain.
Now, if it rained last night, then the lawn is wet. It didn't rain last night, therefore the lawn is not wet. Valid or fallacy?
Also valid. No, not necessarily.
Fallacy.
Not necessarily, yeah, fallacy.
Yeah, this is a fallacy. Okay, so a prepositional letter is a symbol that represents roughly the kind of thing that is expressed by a simple declarative clause or sentence that does not contain any of the words and or not if then. For example, the prepositional letter P is a placeholder for clauses like Boston is the capital of Nebraska, or red is a primary color. Yeah, sentences that is either true or false. Yeah, so we have prepositional letters P, Q, and R. it just like given, okay? We take that. We have P, Q, and R, 4 propositions, 4 simple clauses that render true or false. Right. This is not actually important. Yeah, and each sentence, that simple sentence, gives a truth value, true or false. And we have an interpretation function. Sometimes we just called it interpretation. That maps each prepositional letter to the truth value. Okay? So, actually, we can describe our whole world around us in this way. For example, Tamar sits against the blue wall. True. Sonia wears glasses. True. Masha doesn't wear glasses. False. Right? And if we gather those sentences into a well, all together, yeah. If we have this set of those sentences, we actually get a description of the world around us. Yeah, do you understand what I'm saying about? You can describe the world around us in these sentences. Leonia is not in Israel, true. Yeah, and we can have an unlimited number of these clauses that would describe the world around us. So P, Q, and R are these short clauses describing the world, and they give the true value here. So with respect to interpretation, certain clauses are true or false, which actually means that in this world, sun is bright over our heads and sea is blue somewhere in Tel Aviv. And I don't know, and we had Yom Kippur 2 days ago. Was it 2 days? And this is true. Yeah, and okay. And it's sort of a function, yeah, an interpretation that yeah, that helps us to describe the world around us. Yeah, and you remember that a propositional letter is a simple sentence. And it is taken by itself a formula. Okay? So we have syntactic rules of formation of the sentence, and we have semantic rules of formation of the meaning. Syntactic rules specify how to build our short sentences, how to build these formulas in propositional logic. And semantic rules specify how we interpret them, how we map them to true or false. Right. Okay. And as we assign truth value to the sentences, these short sentences, to the formulas actually, we introduce a denotation function. Denotation gives us a denotation to every formula of the language, meaning that we understand what is behind this sentence. Yeah. For example, when we're saying the sea is over there in Tel Aviv, we can imagine that seaside, I don't know, the Kur in going all over all along the seaside in Tel Aviv. So we have something, we have a meaning behind what we're saying. And this is called denotation. And we use double square brackets. This is like, one moment. This goes like in this way, double square brackets. And these are called semantic brackets, because this is what we use to denotate our small sentences, to get the meaning out of our small sentences, out of our formulas of language. Right? So now we have this convention. For any well-formed formula, which is well-built short sentence, okay, well-built clause. Well-formed formula phi of propositional logic, let the meaning of phi, square brackets, stand for the denotation of phi with respect to interpretation function, which we'll call I. I is an interpretation function. So phi so far is a meta variable, yeah, just a symbol that stands for a formula of propositional logic. Yeah, if you follow, yeah, formula our short clauses. So sometimes phi is written like in this way, And yeah, it's like we agreed that for propositional letters we use P, Q, and R. We just agreed that's a convention. And for well-formed formula, we use phi and psi. And these are meta variables. And phi and psi are not themselves part of our matrix describing our word. Yeah. These propositional letters, these sentences, short sentences, are parts of our matrix describing world around us, which here called L prop. Yeah, this is this matrix. Yeah, this is how they call it. And phi and psi are not part of this matrix. Yeah, they're part of meta language that we use to talk about this matrix. Right. Now, this matrix, which is over here given in square brackets, we called it I1 because it's an interpretation. It's first interpretation that we started talking about, so that's why I1. Then, for example, the denotation, we use square brackets, of P under this function, under this interpretation, I1 is true. Because we see here P leads to true, renders true value. Yeah. So you see that interpretation functions and denotation functions, they map formulas to their truth values. It's like the C is in Tel Aviv. Is it true or false? It's true. Yeah. So we came to the truth value. Yeah. One moment. So there is the difference between interpretation and denotation, but I don't quite capture it over here right now, and I don't quite see so far if we need it. If you see it, tell me. So we're talking about propositional languages, but I think it's meant that we can change this convention and use other letters, for example, and so we'll have different propositional letters, and or we can use the same letter for different purposes, but so interpretations will differ. Yeah, but once the interpretation function is fixed, the denotation, which over here is a denotation, under this interpretation is fixed too. So we come to a semantic rule. If phi is any prepositional letter and I is any function from preposition letters to truth values, then we can write it in this way. Yeah, so denotation of phi under interpretation function E is E of phi. So, for example, denotation of P under the interpretation function E is E of P. If E of P is true, then denotation of P under the function under the interpretation E is true as well. Okay, well, so far so good? Yeah, do you follow? So what is exercise 4? What is the value of E1 of R? E is defined like this. What is the value of E1 of R? Look here. We're looking here. Okay. So this is E1. What is E1 of R? Think. Any answers? Look, R in this interpretation goes to false. Okay? No C in Beersheba. R is Beersheba, for example. We're talking R is C is in Beersheba. Yeah, this is false. So under this interpretation, R is false. So the meaning is false. Okay? Let's say we've got PF. I'm drawing some E2. Okay, this is E1 and I'm drawing E2. Q true, R true. Yeah, this is interpretation E2. And under this interpretation, P might be, I don't know, let's say, apples grow on a banana tree. Q might be, I don't know, water is wet, and R might be sea. The sea is in Tel Aviv. Okay? So now give me E2 of Q. What is E2 of Q?
True.
True, yes, true. Seva, Lenya, Tamar, is it clear why E2 of Q is true?
I mean, when you explain it, it is, but then I cannot
Look, you've got
use
this
it myself.
matrix. You've got this matrix, okay? Where you've got certain statements, yeah? And each of these statements got its true or false value, yeah? And this is a description of a world, which's got a certain set of statements. And when you take this function, it might be called anyhow, but we call it, this function, we called it E. And this function we called E1, and this function, this interpretation, okay, of the world, we called E2. It's just the name we gave it. And in this interpretation, in this image of world, in this understanding of world, the meaning of Q, which is a certain statement like water is wet. Okay, in this universe, water is wet renders true meaning, true value, right? So that's why we say in this interpretation, in this universe, in this matrix, okay, Q, which is a certain statement, renders a true value. Okay, got it?
So the I2 or I1 refers to the set of definitions.
Yeah. I1 of P is true. I2 of R is true. IP of I2 of P is false. Yeah, the sea is not in Beersheba in this universe.
All right. Okay.
Right. Okay. Okay. It's just a way to look at the world. Okay.
Yeah, like when you explain it, it does make sense, but then it's hard to actually put in practice
It
because
really demands some breaking of
the
brains.
the signs and the marking of it in a such logical way is difficult for me. Okay, I also wanted to say that unfortunately I would have to go at 9, which is in a minute, because I have to go to my brother.
Okay, I see. Well, we'll continue for half an hour more.
Mhm.
You'll have a recording.
Mhm.
Right. Now,
Thank you very much.
thank you for coming. Now, what is the value of again denotation? Yeah, denotation are under the E1. What is the value of denotation of R under the E1 function, interpretation 1, in the universe E1. Guys, well, looking here, here's our E1. Here's our interpretation 1. Here's our universe, where we search for denotation for R. So what does it equal?
False.
False, right. Here. Okay? Any problems with that? Do you need a more detailed explanation why, Lyonya? So you just look at the interpretation matrix, you find this R, and you find its value. And E of R is the same as R denoted in E, okay? They're equal. It's just the same, just different way to write it, but it's the same. Right. And here we've got Boolean connectives. They're logical connectives or just connectives. And these are just logical operators like and. They correspond to those logical operators like and, or, not, if, then, if and only if, which is abbreviated as EFF. Yeah, EFF gives us if and only if. Yeah. So you ask your friend, are you free today or tomorrow? And she says no. Yeah. This means that she is not free today and, because we have and, she's not free tomorrow. And then we have this not P or Q. Today is P, tomorrow is Q. Today or tomorrow gives us P or Q, okay? And now we get this not P or Q. All right, let's go again. P is today. Q is tomorrow. We'll get P or Q. Yeah, and we get this P or Q thing, and we negate it. Not P or Q. So she is not free today or tomorrow. And today and tomorrow. Right? Which is the same, sorry, as not P and not Q. Yeah? And not P and not Q can be written as not P or Q. So the argument is valid in both directions. So not P and not Q is equivalent to not P or Q. And this is the relation that we can express using if and only if. Look at number 10, not P and not Q, if and only if, not P and or Q. Okay, are we good so far? Does this need? Okay, this is good. Now, you ask your friend, are you free today and tomorrow? And she says no. This means that either she's not free today or she's not free tomorrow, or both. So we get P and Q, right? P is today, Q is tomorrow. Today and tomorrow is P and Q. Now we negate it. We get not P and Q, which is not P or not Q. Yeah? And the converse is valid as well. Not P or not Q equals to not P and Q. So we've got this 13 example, not P or not Q, if and only if, not P and Q. Right, and this is called De Morgan's laws, which is just the name of those two things about and or and not. Yeah, we're going to talk about it later. So we're talking about prepositional letter, which is a simple clause, P, Q, and R. Yeah, the C is in Beersheba. The cat is meowing. And this is called an atomic formula. And if we connect them with connectives like P and Q or R, we get a complex formulas. So for example, we have this and symbol, which is also can be written like this. Yeah, this is and. And then we have this symbol, which can be written as this, which is or. So this is and this is or. Yeah, these are binary connectives because they join two formulas together, P and Q, P or Q. Yeah, then we have this symbol, which is negation. Sometimes it's written like this. And this is negation. And negation is called unary connective because it applied to a single formula to produce a new one. We can say not P. We took an atomic formula and we got a new one. Oh, we take a formula, any formula, and we apply negation and we get a new one. So, and or are binary connectives because they join two formulas. Negation is called unary connective because it applies to one formula, either atomic or complex. Yeah. And these are called operators. So far, so good, right? So, Susan doesn't volunteer on Monday. Let's say P. Let's say P is the sentence, Susan volunteers on Monday. Okay, this is P. And then we can represent the sentence, Susan doesn't volunteer on Monday as negation P. Okay? So Susan volunteers on Monday, and then we apply negation, and we get Susan doesn't volunteer on Monday. Okay. Ginger is a cat. Let's say it's a Q. Yeah, Q is Ginger is a cat. Now, you apply negation, and what do you get? Guys, give me.
Ginger is not a cat.
Ginger is not a cat, yes. Negation Q is Ginger is not a cat. So, if something is a formula, some phi is a formula, then negation phi is also a formula. So, we have a sentence, we apply negation, and we get a sentence, actually. That's what is it about. It is about. So, and we call it negation of phi. So, Ginger is not a cat is a negation of Q. Yeah, Q is Ginger is a cat. Negation of Q is Ginger is not a cat. So far, so good? Right. Now, if, look, if P is true, then negation P would be
False.
false. Yes, because Ginger is a cat. If Ginger is indeed a cat, then it is a true. It's true. Its value is true. But Ginger is not a cat. We're looking at a cat. In this universe, it's false, right? So negation of a formula. Yeah, and then we get this truth table. This is called a truth table. Yeah, so we've got P and negation of P. If P is true, then negation of P is false. If P is false, then negation of P is true. Okay? This should be clear, right? Even I got the meaning of it like from the first time. There is another table which is more brain-breaking, but we'll get there later. So if P is true, then negation of P is false. If P is false, then negation of P is true. So this is the semantic rule about negation. If phi is a formula, so if it's a sentence, no, we're calling it a sentence, but in propositional logic, it's a formula. If phi is a formula, then denotation of negation of phi Sorry, another direction. In interpretation E is true if the denotation of phi in the interpretation E, in the universe E, is false. Okay? Do you understand this thing? This takes our matrix, our vision of the universe that we called E, yeah? And there is this phi in that matrix with certain truth values, and phi there goes to has, for example, false meaning. Yeah? And when we denote phi in the universe E, we get the false value. Negation of phi, however, in the universe E, always gets true value in this case, and vice versa. If phi has true value in this universe, the negation of phi would get false. Yeah, if we denote it, it would get false value. So far, so good? Yeah. Right. Okay. So now for more terms, if we use and, P and Q, X and Y, Peggy and Maggie, whatever, Monday and Wednesday. This expression is called a conjunction. Yeah, you hear the actual linguistic terms here, a conjunction. Or logic goes with them as well. Or expression like P or Q, Peggy or Maggie, Monday or Wednesday is called a disjunction. Right. Susan volunteers on Monday and Wednesday. Monday and Wednesday is a conjunction. All right. In fact, it's actually two formulas, two atomic formulas, two prepositional letters. Yeah. One prepositional letter P represents the sentence Susan volunteers on Monday. And another prepositional letter Q represents the sentence Susan volunteers on Wednesday. Here's our two atomic formulas. Now we join them and get P and Q, which means Susan volunteers on Monday and Wednesday. Yeah, this is in propositional logic a conjunction of two sentences. Susan volunteers on Monday and Susan volunteers on Wednesday. Yeah. If you ever were taught syntax, for example, Russian syntax, they usually explain it that we've got this preposition, yeah, пропозиция, and preposition is all those atomic sentences like today is Friday. Banana is yellow. And actually, all adjectives, well, every predicate gives us a preposition, and even an adjective gives us a preposition. For example, water is transparent, more or less, but transparent gives us a preposition. So I remember this like nightmare when we were explained that it was like I don't remember, but maybe third grade at the university, third year, with the syntax, when we were supposed to like take a text and make a set of prepositions out of this text. And you had to remember that when you had the sentence, the gray dog came to a green house, you have the preposition, the dog is gray, the house is green, dog came to the house. So 3 propositions in one sentence, something like that. Yeah. That was actually fun, but as we had an examination to pass, that was a bit of a nightmare. Right. So, and if P and Q are formulas, then P and Q is also a formula, just not an atomic one. Right, and now is another truth table, which is not that obvious. Let's look at it. Yeah, we're talking about this thing. We have here P, Q, and P and Q. Okay? Now, look at my hands. If P is true and Q is true, then P and Q is also true. If P is, oh, this was one is obvious. There is another one which is not obvious. P is true and Q is false, then P and Q is false. For example, if P is, let's say, the dog is gray, and Q is the dog meows, then the gray dog meows is false, okay? Even if the dog is indeed gray. So when we have a conjunction, any false here gives us false in conjunction. Like if the dog is white and not gray, but it meows somehow, then still the gray dog meows is false. And if both, then it's obviously false. Right. Now, you see this is how it's written. Yeah. Double brackets is denotation of the complex of the conjunction phi and psi in the universe E, in the interpretation E, is true if phi is true and psi, denotation of phi and denotation of psi is true and false otherwise in any other case. Right. And this disjunction, yeah, which is written like with this sign. It's read like P or Q. So the truth table gives us if P is true and Q is true, P or Q is true, if there is truth on either side, then P or Q gives us true. And if both are false, only in this case, it's false. Yeah. So, I don't quite remember this inclusive disjunction. I need to think. So, Susan volunteers on Monday or Wednesday. Can you think that Susan volunteers either on Monday or Wednesday, but not both? If not both, then you would get an exclusive interpretation. But here we've got inclusive because it might be or both. Right? True, true. It can be true, true. So it's true if both true. If Susan volunteers on Mondays and on Wednesdays, it's still true. It holds true. That would be inclusive disjunction. Exclusive disjunction is when we get but not both. Is when true, true gives us false. Okay? Right. And sometimes exclusive disjunction is written X or OR. X or R. Yeah, this would be exclusive. Right. Okay, I suggest you write the formula, semantic rule for exclusive disjunction yourselves. I don't think, I think we can skip it in class. So, and now where we actually start breaking our brains is when negation comes here. So we've got P and Q, but not P and Q. Yeah. I know that's not the worst. Okay, at some stage, it would be brain breaking, I promise, but not probably so far. I suggest that we start with negation next week, okay? So far, as a homework, I'd suggest that you go through these conventions again and just try to write it down. Yeah, to get used to those ways to formulate how we see our world. Try to think of examples for each situation in the truth table. For example, I don't know, this gray dog, mouse, or so on. Yeah.
For all tables, since
I think we need to go through a conjunction, disjunction, and exclusive disjunction. Yeah, this is where we should just repeat it to be easy with that material, to start with negation. Yeah, I think this is it.
Thank you very much.
Thank you.
Thank you for coming. Thank you. Hopefully this was clear, right? Yeah. This is just marvelous. Okay, have a good day, and I'll see some of them tomorrow, and some of you tomorrow, and some of you next week. See you.